In this video, we discuss displacement mapping and subdivision. We're going to be using a simple cube and a simple plane object for this lesson. I'm going to go to Create menu in the Material Manager, Arnold, Surface, and create a brand new utility shader and assign it to the cube for now. Also, let's run the IPR and open up the utility shader and change the shade mode to Lambert and overlay mode to polywire. Now we can see the edges of our geometry in the render, which can help us to understand the subdivision parameters a bit better. I'm going to right click on the cube, go to C42A tags and add an Arnold parameter tag. Now go to the subdivision tab. First off, you have the subdivision type, which is non-linear and cat-Clark. We have iteration, which specifies how many times the mesh should be subdivided. So when the type is set to none, there would be no subdivision, obviously. When set to linear, as you increase the number of iterations, you are adding more polygons to your geometry without changing or compromising the shape of the geometry. Now, when the iteration is set to 0, there would be no subdivision. When I increase it to 1, we have generated 4 faces off of each face. When I increase the iteration to 2, we have quadrupled the number of polygons again. Go to 3, we have quadrupled the number of faces again. So each time you increase the iteration by 1, you will end up with 4 times more polys compared to before. But in linear mode, you keep the original shape of the object. Let's change the subdivision type from linear to cat-Clark, and immediately we have a sphere instead of a cube. The cat-Clark algorithm is used to create smooth surface by recursive subdivision surface modeling. So as I increase the iteration, I'm not only adding more geometry, I also make the geometry rounder and overall smoother. Let's set the iteration to 3. For displacement maps that you get from sculpting tools like ZBrush or Mudbox, you normally need to change the subdivision type to cat-Clark. Then we have adaptive metric, which allows us to have some level of adaptiveness in our subdivision. So for example, based on how close or far we are away from our object, we can have more or less iteration applied automatically. At the moment, it is set to auto, and as I increase my adaptive error to, let's say, 60, you can see we have smaller amount of polys. And if I get away from my cube and rerun the IPR, because we are far away from our cube and we don't possibly need as much detail as before, we're gonna have smaller iteration value and therefore less polygons. If I get closer to my cube and run the IPR again, we're gonna have more iteration and polygons again. Let me just get away from the cube and rerun the IPR. Now as I decrease the adaptive error value, we are gradually decreasing that adaptiveness, and at 0 we have no adaptiveness no matter what. Let's get back to the camera again. Also, we have 2 adaptive modes beside auto: edge length and flatness. When set to flatness, the curvature of the mesh in pixels is the feature used to choose the adaptive subdivision level. When using edge length, the length of the polygonal edges in pixel is used. And when set to auto, flatness will be used when no displacement map is applied, and edge length will be used when a displacement map is applied to the mesh as well. Then there is adaptive space with raster and object modes. Raster corresponds to adaptive subdivision in raster space, and object corresponds to adaptive subdivision in object space. Now, when instancing, you should use the object mode, and when you have only one object, the raster mode will work. You probably don't need to change this option unless you have some instancing going on in the scene. Also, you can read about these options in the Arnold Sport website. We have UV smoothing, which controls the algorithm used to smooth the UV vertices in the mesh when you are subdividing it. So pin corners pins the 4 corners of our UVs, and the rest of our UV might move as we subdivide our mesh. Pin border will pin all the edges of our UV. Linear will pin everything, so the UV will stay as it was before subdividing, and smooth will basically move the UV vertices as we subdivide our mesh. No pinning basically in this mode. Also, if you noticed any faceting happened in your specular highlights, when you have an isotropy, you can enable smooth tangents to get rid of the faceted look by enabling smooth tangents. There is this ignore frustum culling. If you go to the render settings main tab and under the subdivision, we have this frustum culling feature that we can enable it, and in this case only the polygon faces that are in the camera view will be subdivided, and anything out of the camera view will not be subdivided. Let me show you how this works. I'm going to unhide this big plane and hide the cube for now and assign the utility shader as well to the plane so we can see how the polygons are being subdivided. Now add an Arnold parameters tag and increase the iteration type to linear and 3. If I get out of the camera in the viewport, and in the IPR make sure the active camera is the default viewport camera, back to the render setting now. Let's say I want to make sure only those polygons that are visible to this camera will be subdivided so we can save some resources on our machine. Simply enable frustum culling and define that camera as the dicing camera. Now, as it is visible in the IPR, only those polygons that are in the viewing frustum of the camera are subdivided. Frustum padding allows you to add some safe padding to the frustum. So if I add like 30 centimeters of padding, some of the out of frustum faces will be subdivided as well. This max subdivisions value here allows you to define a limit to the number of subdivision iterations in your scene. Thereby, no object can have a bigger subdivision iteration than the defined value here. Back to the Arnold parameters tag, we had this ignore frustum culling, which would disable global frustum culling for this particular geometry. Now that we have this foundation about subdivision, let's discuss displacement mapping, which allows you to create real geometric details based on a texture. The difference between displacement mapping and bump mapping is that bump mapping was just an illusion, right? We wouldn't alter the geometry, but displacement mapping actually creates and alters the geometry. And it is obviously much more realistic. Now let me show you how displacement mapping works. I'm going to hide the plane and unhide the cube. Start by creating a new standard surface shader, and I'm going to rename it to normal displacement or something like that. Open it up and open the network editor for this shader. As you can see down here, we have the Arnold displacement port. I'm going to press Ctrl Tab and search for displacement. And we have this displacement node. Let's add it to the scene. This node contains two types of displacement mapping, normal and vector. Normal displacement map is the more traditional one when you have a grayscale image and you want to add displacement based on that grayscale texture. And vector displacement can also displace the mesh in different directions besides only up and down that we have with normal displacement mapping. When you add a displacement map node, it will automatically be set as the Arnold displacement shader. You can connect it manually as well. The next thing would be to define the grayscale image which we want to drive our displacement mapping with. So add an image node and load this brick disp map. And let's see it on the cube. It looks like to be too small, so I'm going to set the U and V scales to around 0.5. And set the standard shader as the beauty shader. As we are in ACES, I'm going to change the color space to utility raw as this is a data map, and we should have done that with the bump maps in our previous lesson. So I forgot that, but do that as well. Now connect the output of the image to the displacement input of the displacement node. The amount of displacement mapping is too much. That's why we see nothing relative in our render. Select the displacement node and decrease its scale, which is the amount of displacement mapping, in this case to something like 0.1. Obviously, we don't have enough subdivision to get enough detail. So select the Arnold parameters tag and increase the iteration to about 8. I can increase the iteration number to get more detail or decrease it to decrease the overall detail. In this case, something like 8, 9 would be enough. Now, if I wanted to preserve the cubical shape of my base geometry, I can change the subdivision type to linear. When we do that, there is something wrong with the displacement mapping. If you go to your displacement tab of the Arnold parameters tag, you have a parameter called bound padding. Padding defines how much to extend the bounding box of the object so that it can include any additional displacement coming from the displacement shader. So when the padding is set to 0, because we don't have big enough bounding box, we see this artifact in our render. By increasing the padding and extending the bounding box of our geometry, we will be able to get our displacement mapping the way it's supposed to be. Use this value sparingly, something like 10-20 centimeters of additional padding will be enough here. Now, if I get back to my shader network editor and select displacement node, here scale controls the amount of displacement. So if I go to 0.2, we are going to get a larger displacement map. Also, you can use negative values, which will invert the effect of displacement. In this case, I'm going to set it to something like 0.05. We have scalar 0 value, which is applied as a shift to the displacement amount. It defines the value of the displacement map that is considered to be 0 displacement. By default, it is set to 0, so the black values of the texture are not going to get any displacement, so 0 displacement, and everything brighter is going to be displaced to the outward direction. When set to 0.5, 50% gray will be 0 displacement map, darker values in the texture will be displaced inward, and brighter values will be displaced outward. And when set to 1, white pixels will have 0 displacement and darker values will be displaced inward. Let's set the scalar value to 0.5 for now. Also, let's select the Arnold parameters tag that is applied to our cube and see what other displacement related parameters are under the displacement tab. We have the height, which is like the scale value in our shader, and it controls the amount of displacement mapping in conjunction with the scale value. We discussed padding. We have another scalar 0 value, which works like the one in the shader. We have auto bump, and as soon as I enable it, we get more details. Auto bump puts the high frequencies of a displacement map into the bump attribute so that you do not need as many subdivision iteration values to get really high quality and high detail displacement mapping. And I suggest to have it turn on to get higher quality displacement mapping, especially with normal displacement mapping. Also, we have vector displacement mode. Let me hide my cube object and unhide this smaller plane. I'm going to create a new Arnold standard surface shader and rename it to vector displacement and assign it to the plane. Open its network editor. Now search for displacement map, add one and connect its output to the Arnold displacement port. By the way, if you don't see this port, simply click on this red corner of the main group and you can find all the available ports, including Arnold displacement map. Simply click on it to be added. Now add an image node and load this ear texture and connect it to the displacement input of the node. There is nothing particular in the render. Let me stop the IPR. I'm going to add an Arnold parameter tag to the plane. Go to the Subdivision tab and change the type to cat Clark and increase the iteration to about 5. Now we are ready to see some displacement map, but if I run the IPR, we still get nothing. Let's get back to our network editor and see what's going on. I mentioned that the difference between normal and vector displacement is that in normal displacement, we only have 2 directions, up and down. So we can raise the geometry or lower it, but we can't move it in any other direction. But with vector displacement, we can actually move our geometry in different directions. Let's select the vector displacement node and change the vector space to tangent, because that's the way I generated this ear displacement texture. The order should be X, Y, Z, and reduce the scale to something like 0.3. Scale here controls the amount of displacement mapping, obviously. Also select the Arnold parameters tag, and under displacement, change the padding to 10-20 centimeters. Now, as you can see, we have a perfect ear geometry in our scene. Now let's discuss different parameters that we have in the vector displacement node. We have scale, which controls the amount of displacement map. Higher values yield stronger effect. We have this signed checkbox. If you have a 32 or 16-bit input map, this should be unchecked. But if you have an 8-bit input, you can check this signed option to get more info out of your map. In this case, I have a 32-bit image, so I can keep it unchecked. Then there is vector space, world, object, and tangent. So based on how you generated the displacement texture originally, you can choose your desired coordinate space. We have tangent, which is the input attribute for connecting a tangent-based vector displacement map. You can change the channel orders and flip different channels. I wouldn't be able to cover every little detail practically here. It would go on forever, but I refer you back to this tutorial on Arnold website, which explains the workflow from scratch on how to generate vector displacement maps and how to apply them. It's called rendering displacement maps from Cinema 4D. So that's about subdivision and displacement mapping in Arnold for Cinema 4D. See you in the next video.